A silent giant governs the city of stars we call the Milky Way. At the core of nearly every major galaxy sits a supermassive black hole, an engine of unimaginable power. We often see them as cosmic mysteries, profound wells of gravitational force. Yet these dark hearts hold a secret. They are not just forces of immense power, but the hidden architects of the universe itself. By the end of this journey, you will see how these invisible engines sculpt galaxies, ignite stars, and write the rules for cosmic evolution. How does a force of pure gravity create the delicate spirals we admire? What stops entire galaxies from fading too soon? The answers lie in a dynamic and beautiful dialogue between darkness and light. What does it mean that our home galaxy is shaped by such a mysterious and central presence? 4 million solar masses of pure gravity sit at the heart of our galaxy. This is Sagittarius, a star, our local supermassive black hole. It is not simply a bigger version of the black holes formed from collapsing stars. It is a different class of cosmic object entirely, a foundational pillar of galactic structure. Think of it not as a resident, but as the keystone in an arch. Remove it, and the entire structure's stability changes. These supermassive entities are thought to have formed alongside their galaxies in the chaotic infancy of the universe, growing together in a shared destiny. They are the anchors around which the grand spirals and majestic ellipses of the cosmos take shape. As Nobel laureate Andrea Ghez discovered through decades of observing stars whip around our galactic center, that central point is where the action is. It is the key to understanding the galaxy as a whole. But how does an object famous for trapping light exert such a profound influence? The secret lies not in the darkness of the event horizon, but in the furious activity just outside it. Here, matter does not simply vanish. Instead, gas and dust from the surrounding galaxy are pulled into orbit, forming a swirling, flattened disk called an accretion disk. This disk is a galactic furnace. Friction and immense gravitational forces heat this material to millions of degrees, causing it to glow fiercely across the electromagnetic spectrum and even blast out jets of energy. It is this powerful release, generated by the black hole's immense gravitational influence, that allows it to reach out and touch every corner of its home. This central engine, humming with gravitational might and radiant energy, sets the fundamental rhythm for the entire galaxy. Its presence dictates how stars move in the dense core and how vast rivers of interstellar gas flow inward. This dynamic establishes the first rule of a lifelong cosmic dialogue, a partnership that begins not with an end, but with an unexpected act of creation. To understand this ancient partnership, we must travel back to the cosmic dawn. The early universe was a simpler place, a vast expanse of darkness punctuated by the faint glow of the first stars and the primordial gases from which they formed. Within this sea of potential, tiny fluctuations in density acted as seeds. Gravity began its patient work, pulling wisps of gas together into larger and larger clouds. But something remarkable happened in the densest cores of these collapsing clouds. Not only did the first stars ignite, but in some regions, the gravitational collapse was so direct and so intense that it bypassed stardom entirely. It forged something else, a direct gravitational pit so deep that light could not escape. These were the primordial seeds of the supermassive black holes we see today. The prevailing theory of co-evolution suggests these dark seeds and their embryonic galaxies grew up together, side by side from the very beginning. Each influenced the other's development in a constant feedback loop. For decades, this was a compelling idea, but we lacked the evidence to see it in action. Then the Hubble and later the James Webb Space Telescope peered back to when the universe was less than 1 billion years old. What they found was astonishing. They discovered quasars, the intensely bright cores of distant galaxies, powered by black holes already weighing billions of times our Sun's mass. These beacons of light, fueled by incredible activity, existed in an era we thought was far too young for such colossal objects to have formed. Their existence implies a period of rapid, almost explosive growth right at the start, a race between the galaxy and its dark heart. This discovery paints a picture of deep symbiosis. The young galaxy, rich with gas, provides the material that sustains the growing black hole. As the black hole gathers this material, its accretion disk blazes with the energy of 1 trillion suns, becoming a quasar. But that energy does not just radiate out silently. It pours back into the galaxy with tremendous force. This is the crucial feedback. That outpouring of energy can compress surrounding gas clouds, triggering furious waves of new star formation, essentially using its power to build the galaxy's stellar population. Yet, in a fascinating paradox, that same energy can also push gas away, heating it and dispersing it so thoroughly that it halts star birth entirely. The black hole, through its presence, becomes the regulator of its own environment. So which came first, the galaxy or its central black hole? The question remains a vibrant frontier of research. Some models suggest the black hole seeds formed first, from the direct collapse of giant gas clouds. Others propose they grew from the foundational objects of the very first, incredibly massive stars. The truth may be a combination, but what is undeniable is their intertwined fate. They are bound together in a gravitational dance that began over 13 billion years ago. This ancient bond, forged in the fires of the early cosmos, sets the entire framework for everything that follows. It establishes the rules for a lifelong dialogue, a conversation between creation and control that continues to this very day in galaxies across the universe. And sometimes that conversation can become a shout. The most powerful conversations in the universe begin with a simple act, a black hole having a meal. But this is no tidy affair. Picture, if you will, a cosmic giant that is a profoundly messy eater. As vast rivers of interstellar gas spiral inward, they do not fall silently into the dark. Instead, they collide and compress, forming a furious, flattened whirlpool of superheated matter called an accretion disk. This disk, glowing with the heat of millions of degrees, is where the black hole's true power is unleashed. It transforms gravity into light, blasting out a torrent of radiation across every wavelength, from searing X-rays to long radio waves. This radiant outburst is the black hole's first and most direct voice. It speaks to the galaxy through a process astronomers call radiative feedback. Imagine a vast, cold cloud of gas, the very nursery where new stars are born. Now bathe that cloud in the intense, constant glare from the central engine. The gas heats up, its atoms move faster, resisting the gentle pull of gravity that would normally allow it to collapse and spark new suns. In this way, a feeding black hole can place a gentle but firm hand on the galaxy's thermostat, preventing it from turning all its fuel into stars too quickly. It is a regulatory mechanism, a way of pacing the galaxy's growth. Yet, the black hole has another, even more spectacular way of making its presence known. Not all the infalling material reaches the event horizon. Some of it is captured by immense magnetic fields, twisted and accelerated into two narrow, opposing beams that scream outward at nearly the speed of light. These are relativistic jets, cosmic blowtorches that can punch through the galaxy for hundreds of thousands of light years. We see them with radio telescopes as brilliant, extended lobes, vast bubbles of energy inflating in the intergalactic medium. These jets are the black hole's shout. Where they plow into the surrounding gas, they stir it violently, injecting turbulence and heat. They can compress gas in some regions to trigger star birth, or they can blast it away entirely, clearing out vast cavities. This dual-channel feedback, the steady heat of radiation and the focused fury of the jets, is how a black hole holds a conversation with its home. It is a dialogue of creation and limitation, of stirring the pot and then calming it down. But this raises a profound question. What happens when the conversation turns into a command, when the central engine decides the galaxy's story of star formation must come to an end? This leads us to one of the most significant puzzles in modern astrophysics, the mystery of galactic quenching. The vibrant star-forming galaxy we see today could have a very different future. It is a cosmic metamorphosis, a slow transformation from a brilliant blue spiral, alive with stellar nurseries, into a quiet red elliptical where the fires of star birth have gone out. This profound change is not a random fade to black. It is often a deliberate act orchestrated by the galaxy's own central engine. When a supermassive black hole enters a phase of intense activity, its feedback can do more than just regulate. It can quiet the process of star formation, entirely an event astronomers call quenching. Think of a galaxy as a vast reservoir of cold, dense molecular gas. This gas is the raw material for new stars. For stars to form, these clouds must collapse under their own gravity, a process that requires them to stay cool and calm. Now unleash the full voice of the central black hole upon this reservoir. Powerful jets and intense radiation flood the galactic environment. They do not just warm the gas. They superheat it, stirring it into a turbulent, energetic state where gravity cannot gain a foothold. In more extreme cases, these outflows can physically push the cold gas right out of the galaxy, stripping it of the very fuel it needs for its future. It is a powerful form of cosmic feedback. As astronomer Timothy Heckman once described it, this process is akin to a form of galactic self-regulation. The central engine in its most active state can end the very cycle that sustains it. This idea solves one of the great observational puzzles in the cosmos, the clear divide between two families of galaxies. On one side, we have the blue spiral galaxies rich with young hot stars and the glowing gas of ongoing creation. On the other, the red elliptical galaxies populated by older, cooler stars with little sign of new stellar life. For a long time, this bimodality was a mystery. What stops a spiral from making stars forever? The answer appears to be written in the correlation between the mass of a galaxy's central black hole and the properties of the galaxy itself. The energy released by the black hole seems exquisitely tuned, scaled to the gravitational potential of its entire home. It is as if the engine knows the size of the vehicle it must control. In this light, the black hole is not a destroyer. It is a cosmic governor. By quieting star formation, it prevents a galaxy from burning through all its fuel in a brief, furious burst. It enforces a kind of long-term balance, influencing the demographics of galaxies we see across the universe. This regulatory role is fundamental. But if this were the black hole's only function, the universe would be a far quieter, darker place. For this engine of gravity has a dual nature, and its most surprising role is not to end the story of light, but to help write its very first chapters. The very forces that can silence a galaxy can also ignite its brightest fires. This is the beautiful paradox at the heart of the cosmic engine. While a supermassive black hole's energetic outbursts can heat and disperse gas to quiet star formation, those same outbursts can, under the right conditions, become the ultimate cosmic spark. It all depends on the delicate conversation between the black hole's power and the state of the galaxy around it. Picture a powerful relativistic jet, that focused beam of energy, not as a simple blowtorch but as a cosmic plow. When this jet meets a massive, relatively cool cloud of galactic gas, it does not always scatter it. Instead, the leading edge of the jet creates a tremendous shock wave, a wall of pressure that sweeps through the cloud. This shock compresses the gas, squeezing it to densities where gravity can finally overcome its internal motion. In that moment of intense pressure, pockets of gas collapse, and new stars are born in a brilliant burst along the jet's path. We have witnessed this very process in action. In the nearby galaxy known as Minkowski's object, astronomers observed a jet from a neighboring active galaxy moving directly into a gas cloud. The result was not destruction, but a stunning ribbon of newborn blue stars, a stellar nursery shaped by the jet's impact. This positive feedback reveals a deeper layer of the black hole's influence. The jets and outflows do not just bring heat, they bring turbulence. They stir the galactic pot. While too much turbulence can prevent star formation, a certain amount at the right scale can actually help it along. It can create the dense knots and eddies within a gas cloud that become the seeds for gravitational collapse. So the black hole, through its dynamic activity, does not merely impose a single rule. It sets the conditions for a complex ecosystem. Its role shifts from suppressor to catalyst based on the density, temperature, and dynamics of the galactic environment it touches. This contextual influence transforms our view of the central engine. It is not a simple on-off switch for a galaxy's light. It is a dynamic participant, a regulator that can both pace the galaxy's growth and, in spectacular moments, give it a creative nudge. This creative potential extends far beyond the boundaries of a single galaxy, shaping the very fabric of the space between galaxies. The energy from these central engines inflates vast, magnificent bubbles of hot gas that rise through galaxy clusters, structures so large they defy earthly comprehension. These bubbles are the lasting monuments of the black hole's most powerful cycles, and they hold clues to an even grander narrative, one that connects the fate of galaxies to the largest structures in the known universe. High above and below the bright disk of our Milky Way, two colossal structures loom in near silence. In X-ray and gamma-ray light, they appear as vast, faint lobes, each stretching 25,000 light-years from the galactic center. These are the Fermi bubbles, monumental relics of a long-forgotten outburst from our own supermassive black hole, Sagittarius, a star. They are not made of stars or dust, but of incredibly hot, thin gas and energetic particles, a ghostly imprint of a past event. These bubbles are the direct archaeological evidence of a galactic wind, a powerful outflow driven by our central engine in a bygone era of intense activity. They show us that our galaxy, now so relatively quiet, was once a place of tremendous energy and transformation. This phenomenon is not unique to the Milky Way. In distant clusters of galaxies where hot gas fills the space between member galaxies, astronomers observe similar cavities, immense spherical voids carved into the glowing intergalactic medium. These cavities are often aligned with the jets streaming from a central galaxy's black hole. They are the lasting monuments of historic feedback events, the cosmic equivalent of a fossilized footprint, revealing the shape and power of a force that passed through billions of years ago. These winds and the bubbles they create are far more than just beautiful remnants. They are a crucial part of the galaxy's life support system, composed of charged particles, magnetic fields, and chemically enriched material forged in stellar explosions. The winds act as a galactic circulatory system. They transport energy, momentum, and the heavy elements essential for planets and life far out into the galactic halo, seeding future generations of stars with richer building blocks. But their most important role is one of regulation. By displacing and superheating the surrounding gas, these colossal bubbles create a high-pressure barrier. This barrier physically prevents vast reservoirs of cooler, star-forming fuel from falling back into the galactic center too quickly. Think of it as a cosmic pressure release valve. When the central black hole becomes too active, its outburst inflates these bubbles, which push back against the incoming fuel supply. This limits the black hole's own future activity, and by keeping fresh gas at bay, also prevents the entire galactic core from undergoing a runaway spree of star formation. It is a brilliant, self-regulating cycle. The engine's most powerful expressions create the very conditions that will eventually encourage it to quiet down. This cyclical rhythm, written in the faint glow of X-ray bubbles and radio lobes, tells us that the dialogue between a black hole and its galaxy is not a linear story with a single climax. It is a recurring conversation, a pulse of activity and rest that shapes a galaxy's evolution over eons. To understand our place in the cosmos, we must learn to listen for that pulse, to decipher the rhythm written across deep time. This rhythmic pulse of activity and quiet is the heartbeat of a galaxy's long life. A supermassive black hole does not shine with a steady light, but in dramatic, episodic bursts. We call these outbursts the active galactic nucleus, or a GN phase. It is a period of cosmic feasting when a rich supply of gas finds its way to the galactic center, swirling into the accretion disk and igniting the central engine. From our distant vantage point, this transforms the galaxy's core into a brilliant beacon, visible across the universe as a quasar or a Seyfert galaxy. For tens of millions of years, this engine blazes, its feedback shaping everything around it, but this very power sows the seeds of its own dormancy. The intense radiation and powerful jets generated during the feast act like a cosmic wind, pushing away the surrounding gas or heating it to a state where it can no longer easily fall in. The black hole, in its most active state, eventually starves itself. The fuel supply is cut off, the brilliant accretion disk fades, and the engine enters a long, quiescent phase. Our own Sagittarius, a star, is in such a quiet period now, a slumbering giant after a past meal. This cycle of feast and famine creates a self-regulating feedback loop of astonishing elegance. The active phase regulates the galaxy, pacing star formation and enriching the surrounding space. The quiet phase allows the galactic environment to recover, for gas to slowly cool and pool once more, potentially setting the stage for a future awakening. This duty cycle explains the stunning diversity we see in the night sky. Some galaxies blaze with brilliant, active cores, while others, like our Milky Way, possess only a silent, dark heart. They are not different species, but simply captured in different moments of the same long, cyclical story. The timing of this cycle, however, is not set by the black hole alone. It is deeply connected to the galaxy's place in the wider cosmos. A galaxy living in isolated splendor may experience long, quiet epochs between its active phases. But a galaxy within a dense cluster, a city of galaxies, lives a far more dramatic life. Here, close encounters and even mergers with neighboring galaxies are frequent. These major interactions can funnel vast reservoirs of fresh gas directly toward the central black hole, abruptly ending its slumber and triggering a new, powerful AGN phase. The cluster environment, with its constant gravitational nudges, acts as a master conductor, influencing the rhythm of the cosmic heartbeat. This reveals a profound truth, that the story of a single black hole is inextricably woven into the fate of its entire galactic community, a narrative written on the largest scales of space and time. The scale of this cosmic conversation grows to almost unimaginable proportions when we look at the largest structures in the universe. A galaxy cluster is a true metropolis of the cosmos, containing hundreds or even thousands of individual galaxies. But these galaxies are not floating in empty space. They are immersed in a vast, thin, and incredibly hot sea of plasma, known as the intracluster medium. This gas is so hot it glows in X-rays, and it represents an enormous reservoir of potential fuel. According to simple physics, this superheated gas should steadily lose energy and cool down. As it cools, it should flow inward toward the cluster's heart in what astronomers term a cooling flow. This inward river of colder gas would flood the central galaxies, triggering absolutely monumental waves of star formation, turning them into brilliant, short-lived stellar factories. Yet, when we look at the universe, we rarely see this extreme scenario playing out. The predicted deluge of new stars is missing. Something is preventing it, and that something appears to be a master regulator operating from the very center of the cluster. This regulator is the supermassive black hole at the core of the cluster's dominant central galaxy. Its role expands here from a galactic architect to a cosmic thermostat for the entire cluster. How does a single black hole, tiny on this scale, manage to heat a sea of gas light years across? The answer lies in the precision of its feedback. During its active phases, the black hole's powerful relativistic jets plow into the surrounding intracluster medium. They do not simply pierce through. Instead, they inflate gigantic, buoyant bubbles of ultra-hot gas and magnetic fields, cavities that rise slowly through the cluster plasma like colossal hot air balloons. As these bubbles rise, they stir the surrounding gas, creating vast ripples of turbulence. They also generate powerful sound waves, yes, sound waves in space, that travel outward, depositing their energy as a gentle, distributed heat. This process is a masterpiece of cosmic engineering. The black hole's intermittent outbursts provide just enough energy to reheat the cooling gas, preventing it from ever reaching the densities required for a runaway cooling flow. It is a balancing act of phenomenal scale. We have seen this thermostat in beautiful, direct action. In the nearby Perseus and Virgo galaxy clusters, X-ray telescopes have captured stunning images. They show the superheated intracluster medium, and within it, clear, dark cavities, the bubbles, carved out by the central black hole's jets. Surrounding these bubbles are subtle, concentric ripples, the fingerprints of those immense sound waves traveling through the plasma. This is feedback written across hundreds of thousands of light years. By gently reheating the cluster's gas, the central black hole ensures long-term stability for the entire metropolitan structure. It prevents the cluster from consuming all its fuel in a single, brilliant, and brief burst of star formation, which would leave it a faded relic. Instead, it enforces a slow, sustainable evolution. This large-scale regulation reveals something profound. The energy output of the black hole is exquisitely calibrated, not just to its own galaxy, but to the gravitational well of the entire cluster it anchors. This precise tuning points to a deeper connection, a hidden code written into the fabric of cosmic structure itself. It suggests that the growth of these dark engines and the growth of the luminous structures around them are not just linked by feedback, but governed by a fundamental set of cosmic rules. This precise tuning is not a coincidence but a cosmic signature, scattered across the universe from brilliant spirals to quiet ellipticals. A hidden law of proportion connects the dark heart to its luminous home. It is called the M-sigma relation, and it is one of the most compelling clues we have to the deep partnership between black holes and galaxies. The law is elegantly simple in its statement. The mass of a galaxy's central supermassive black hole is tightly correlated with the velocity dispersion of the stars in the galaxy's central bulge. Velocity dispersion sounds complex, but think of it as a measure of the stellar hustle and bustle in the galactic core, a direct indicator of the depth of the galaxy's gravitational well. In simpler terms, the more massive and dynamically active the central bulge of stars, the more massive its central black hole tends to be. This relationship holds with astonishing precision across galaxies of wildly different sizes and types, spanning an incredible range of masses. A small bulge means a smaller black hole. A giant, puffed-up bulge means a truly colossal dark engine. This is not a vague trend. It is a clean, mathematical line drawn through the data of the cosmos. Why is this so profound? Because it tells us the growth of the black hole and the growth of the galaxy's central structure are choreographed together. They did not evolve independently. Something linked their fates, ensuring they grew in lockstep over billions of years. That something is almost certainly the feedback dialogue we have been exploring. The energy released by the black hole during its active phases must be exquisitely calibrated, perfectly matched to the gravitational grip of the galaxy itself. Too little energy and the feedback is insignificant, allowing runaway star formation. Too much energy and the black hole might push away all the gas, limiting both its own growth and the galaxy's. The M-sigma relation suggests the system finds a perfect balance. The black hole grows until its feedback output becomes powerful enough to push back against the infalling gas, effectively regulating its own further growth and simultaneously shaping the stellar population around it. It is a self-limiting cycle that leaves this precise fingerprint. Discovering this relation was a watershed moment in astrophysics. For the first time, we had quantifiable evidence that a supermassive black hole was not just a passive occupant, but an integral component of galactic anatomy, as fundamental to a galaxy's structure as its spiral arms or its halo. This law points to a universal mechanism, a set of rules that governs the construction of cosmic cities across the universe. The dialogue between the dark engine and the stellar city is not a random series of shouts and whispers. It is a sophisticated conversation that follows a script written in the language of gravity and energy, leaving this elegant correlation as its lasting record. This cosmic law of proportion forces us to ask an even deeper question. If black holes and galaxies grow together, shaping each other's destinies, what does that mean for the very first chapters of the story? How did this profound partnership begin in the earliest darkness? This cosmic law of proportion is written into the very forms we see in the night sky. The majestic spiral of a galaxy like our own, with its delicate arms tracing graceful curves, and the smooth, featureless ellipse of a giant red galaxy, are not random shapes. They are the end results of a long history, a history deeply influenced by the activity of the central engine. That engine acts as a cosmic sculptor, and its most transformative work often begins with a profound creative act, a galactic merger. When two spiral galaxies drift too close together, gravity weaves them into a dynamic dance. Their delicate disk structures are reshaped and stretched. Crucially, vast reservoirs of cold gas from both galaxies are drawn inward toward their merging cores. This delivers a feast of epic proportions to the supermassive black holes at their centers. The result is a spectacular ignition. Both black holes enter an intensely luminous active phase, blazing as brilliant quasars. The feedback from this dual outburst is both powerful and creative. The energetic radiation and relativistic jets act like a galactic wind, clearing away much of the remaining star-forming gas and stirring what is left. This dynamic process disrupts the orderly rotation of the original disks. The stars, no longer moving in a neat, flattened plane, are scattered into a more random, three-dimensional swarm. What emerges from this activity is no longer a spiral. It is a smooth, rounded, pressure-supported elliptical galaxy. This transformative process does more than just change a galaxy's appearance. It directly reinforces the relationship we observe between a galaxy's core and its broader structure. The merger itself delivers a huge amount of mass, growing both the central black hole and the surrounding stellar bulge simultaneously. The ensuing feedback then fine-tunes that connection, ensuring the final product fits the elegant cosmic law. In stark contrast, consider a spiral galaxy like our Milky Way, living in a quieter neighborhood of space. Without a major merger to dramatically channel gas to its center, its supermassive black hole remains relatively quiet. This allows the galaxy to retain its vast, rotating disk of cold gas. Star formation can proceed in an orderly, sustained fashion within the spiral arms, preserving the galaxy's graceful shape across billions of years. The black hole's role here is subtle, a gentle governor rather than a dramatic sculptor. This reveals a profound truth about how galaxies change over time. A galaxy's shape is a record of its most significant life events. the presence of a prominent disk speaks to a history of calm, ordered growth. The smooth form of an elliptical galaxy is a testament to a dynamic past, a past where central black holes were awakened to their full, transformative power. This shaping influence was likely the dominant force in the early universe, a time of frequent interactions and colossal flows of gas. With new telescopes, we are now witnessing these ancient transformations in progress, watching as brilliant, dynamic mergers are gradually shaped into the serene ellipticals we see in the modern cosmos. The black hole in its most active state is the tool that smooths away the spiral's delicate features, leaving behind a monument to cosmic change and the enduring laws of balance. The universe was once a sea of silent darkness, a fog of neutral hydrogen that absorbed light as soon as it was born. Yet within a few 100 million years of the Big Bang, brilliant beacons began to pierce that gloom. These are the quasars of the cosmic dawn, and they are rewriting the story of how everything began. The James Webb Space Telescope has revealed quasars powered by supermassive black holes that already weighed over 1 billion suns when the cosmos was a mere infant. Their existence is a profound puzzle. How could such colossal gravitational engines assemble so quickly in what seems like a cosmic blink of an eye? The standard models of black hole growth, starting from the first massive stars, struggle to explain this rapid inflation. It suggests a different, more dramatic birth. Some of these first black holes may have formed not from stars at all, but from the direct, monumental collapse of gigantic primordial gas clouds. These direct collapse seeds would have been born heavy, perhaps tens of thousands of times the mass of our Sun, giving them a massive head start. Or perhaps the early environment allowed for feeding frenzies of unimaginable efficiency, where gas flowed into the growing black holes at rates that defy modern physics. This was a universe where the rules were different, denser, and far more extreme. In these nascent galaxies, the conversation between the black hole and its home was not a gentle dialogue. It was a primal event. The surrounding gas was abundant and dense, providing immense fuel but also creating an environment where feedback was overwhelmingly powerful. The radiation and outflows from these young, voracious engines would have interacted with their surroundings with incredible intensity. This energy did more than just shape a single galaxy. It performed a service for the entire cosmos. The fierce ultraviolet light from these earliest quasars is thought to have been a primary driver of cosmic reionization. It transformed the atoms of the pervasive hydrogen fog, gradually clearing the universe and making it transparent to light for the very first time. In a very real sense, the first supermassive black holes helped turn on the lights for the universe, clearing the primordial haze and allowing the cosmic dawn to give way to a clear, star-filled sky. Their influence extended even further. By releasing energy and chemically enriched material into the pristine intergalactic medium, these ancient engines seeded the cosmic web itself. They created bubbles of hot gas and channels of influence that dictated where the first generations of stars could form and how they would evolve. The properties of those earliest stars, their sizes, their lifespans, and the elements they would forge were all influenced by the environment these central black holes helped create. Their fierce light, which has traveled for over 13 billion years to reach our telescopes, is more than a beacon. It is a time capsule carrying encoded information about the infancy of the most important partnership in cosmology. To decode these ancient signals, to understand the first words of the conversation between darkness and light, astronomers must employ every tool at their disposal, from space-based observatories to immense radio arrays listening for the faintest echoes of creation. Detecting a cosmic giant that emits no light requires a different kind of vision. Astronomers act as cosmic detectives, assembling a portrait of the invisible from a symphony of indirect clues scattered across the universe. Each wavelength of light tells a different part of the story, revealing facets of its powerful influence. In the quiet radio bands, vast arrays of dishes listen for the faint, ghostly whisper of synchrotron radiation. This is the signature of charged particles spiraling at near-light speed within those colossal relativistic jets, mapping out the engine's most far-reaching outbursts. To witness the fierce heat of the feast itself, we turn to X-ray observatories. They see the universe in energies 1,000,000 times greater than visible light, capturing the searing glow of million-degree gas in the accretion disk and the magnificent, hollow cavities those jets create in the heart of galaxy clusters. But much of this drama is hidden behind thick curtains of cosmic dust. This is where infrared eyes come in. Telescopes peer through that obscuring veil. They see the warm glow of dust heated by hidden active nuclei, and they simultaneously map the brilliant birth of new stars triggered by the engine's feedback, connecting cause and effect. Perhaps the most astonishing direct evidence arrived just a few years ago from a telescope as large as the Earth itself. A global network of radio observatories synchronized with atomic clocks achieved the impossible. It gathered enough data to reconstruct an image of the shadow of the supermassive black hole at the heart of galaxy M87, a dark silhouette against the glowing ring of infalling matter. This was not a photograph of the object itself, but of its gravitational fingerprint, a direct visual testament to its overwhelming presence. The detective work goes beyond light. By using spectrographs to split starlight into rainbows, astronomers can measure the velocity of stars and gas whipping around a galactic center. The faster they orbit, the stronger the gravitational grip holding them must be. These precise measurements of a chaotic stellar dance allow scientists to calculate the mass of the unseen anchor with remarkable precision, applying the cosmic law we see written across the universe. And now we have an entirely new sense with which to perceive these dark giants. Gravitational wave observatories listen not for light, but for the faint ripples in spacetime itself. They have heard the chirp and ring down of stellar mass black holes interacting, providing a dynamic test of how they behave in their most energetic moments. This multi-messenger approach, combining every form of signal from light to ripples in space, is how we build a complete understanding. Each observation is a single piece of a vast, interconnected puzzle. A radio jet here, an X-ray cavity there, a star's frantic orbit, a space-time tremor from a distant event. Together, they refine our theoretical models, helping us decipher the complex rules of the cosmic dialogue. This evolving toolkit does more than confirm what we suspect. It constantly surprises us, revealing that the relationship between a black hole and its galaxy is even more nuanced and profound than we imagined, a partnership with implications for the fate of everything we see. The most powerful laboratories for understanding this cosmic dialogue are not found on Earth, but are built inside the world's most advanced supercomputers. Here, in lines of code and vast arrays of processors, scientists construct entire virtual universes, letting billions of years of cosmic evolution unfold in a matter of weeks. These are cosmological simulations with names like Illustris TNG and EAGLE, and their purpose is profound. They serve as a testing ground for our ideas about how black holes and galaxies grow together. To make these digital universes work, researchers must write the rules of the conversation into the very fabric of the simulation. They create sophisticated mathematical recipes, called subgrid models, that describe how a black hole gathers material from its surroundings and, crucially, how it injects energy back out through radiation, winds, and jets. It is an attempt to translate the theory of feedback into a language a computer can calculate. The process begins with the initial conditions of the early universe, a sea of dark matter and primordial gas. Then the simulation runs. Gravity works its magic, pulling matter into clumps that become galaxies. Within those galaxies, the code governing the supermassive black hole seeds activates. We watch as these digital black holes feed, grow, and according to their programmed physics, begin to speak back to their virtual galaxies. The outcome of these experiments is then compared to the real, observed universe. Do the simulated galaxies have the right range of masses and shapes? Do their stars form at the observed rates, or do they blaze too brightly and fade too fast? Most tellingly, do the simulated black holes and their host galaxies obey the same cosmic law, the M-sigma relation, that we see etched into the real cosmos? The results are strikingly clear. Simulations that lack this black hole feedback mechanism fail. They produce galaxies that are too massive, too blue, and too rich with new stars. Their central black holes bear no meaningful relationship to the galaxies around them, but when the feedback physics is switched on, something remarkable happens. The simulated universe begins to look familiar. Elliptical galaxies appear red and quiet. Spiral galaxies maintain their elegant disks. The black hole masses align with the velocity of the stars in the central bulge, mirroring the law we observe. This consistency is a powerful, if indirect, validation. It suggests the theory of feedback is not just a compelling story, but a necessary ingredient in the recipe for a realistic cosmos. These digital laboratories allow for experiments we could never perform in reality. What happens if we turn the jet power up by a factor of 10? What if black holes grew only from mergers and not from steady gathering of material? By adjusting the recipes, scientists can explore which aspects of feedback are most important for shaping different galactic features. They reveal the black hole not as a passive component added to a finished galaxy, but as an active, governing force from the very beginning. This virtual evidence challenges a simpler view of cause and effect, suggesting that to understand why a galaxy looks the way it does today, we must account for the voice of its dark heart echoing across deep time. This partnership defines our simplest ideas of cause and effect. We naturally want to ask which came first, the galaxy or its black hole, and which one is truly in charge. It is the ultimate cosmic chicken or egg dilemma, playing out on a scale of billions of years. The evidence, however, resists a clean answer. It points not to a linear chain of events, but to a deeply entangled, non-linear feedback loop. The black hole is not a puppeteer pulling the galaxy's strings, nor is the galaxy merely a passive stage for a dark actor. They are partners in a constant, dynamic conversation. Consider a dense, cold cloud of gas, the raw material for new stars. A burst of energy from the central engine can heat and disperse that cloud, slowing star formation. This alters the future fuel supply for the black hole itself. Conversely, that same energetic outburst can, under different conditions, compress other gas clouds, triggering a wave of stellar birth. This new generation of stars will live and eventually enrich the galaxy with more material, some of which may later spiral inward to feed the engine again. It is a cycle of action and reaction where cause and effect blur into a single, ongoing process. This reality asks us to move beyond the search for a single prime mover. Instead, we must view a galaxy as a holistic, self-regulating ecosystem. Within this system, the luminous stars and gas, the invisible dark matter halo, and the supermassive black hole are all dynamic participants. They are engaged in a grand gravitational dance, each influencing the other's steps. The black hole, through its feedback, acts as a central regulator, a cosmic thermostat that helps maintain balance over immense timescales. It prevents the system from either burning too brightly and too briefly or from settling into stagnation. This systemic view is a profound shift in our understanding. It elevates the supermassive black hole from a bizarre curiosity at the center of things to a fundamental component of galactic physics, as integral to a galaxy's life story as its spiral arms or its halo. This idea, born from decades of observation and simulation, continues to reshape our textbooks. It teaches us that to understand the life of a galaxy, we must listen to the entire conversation, not just one voice. And as we refine this view of cosmic ecosystems, we are compelled to look forward, to ask what this enduring dialogue means for the very long-term future of everything the light touches. The cosmic dialogue of creation and control we see today is just one act in a story spanning trillions of years. If we project the timeline forward, far beyond the age of stars, we arrive at a profoundly different universe. The brilliant spirals and glowing clusters of today will have long since faded. The era of star formation will have ended as galaxies exhaust their reservoirs of cold gas or see it locked away in stellar remnants. In this distant, darkening epoch, the universe will be a quiet expanse of cooling embers, where white dwarfs and neutron stars slowly dim against an ever-expanding void. Yet, even in this final act, the supermassive black hole will play a defining role. It will become one of the last significant sources of energy in a cooling cosmos. For eons after the last star flickers out, these dark giants will continue their slow feast. They will gather the final wisps of interstellar material, perhaps from the occasional disrupted brown dwarf or the tenuous wind from a cooling white dwarf. This accretion, though incredibly sparse, will generate faint glows, the last whispers of light in entire galaxies. On timescales so vast they defy human comprehension, an even more profound process will begin. According to Stephen Hawking's theory, black holes are not truly eternal. Through quantum effects at their event horizons, they slowly evaporate, emitting a faint trickle of particles now called Hawking radiation. For a supermassive black hole, this process is achingly slow, taking far longer than the current age of the universe to even begin significant mass loss. But in the deep, cold future, this radiation may represent a final, slow leak of energy back into a universe approaching absolute stillness. Their gravitational influence, however, remains absolute. The supermassive black hole will continue to govern the motions of this quiet galactic expanse. The stellar remnants, white dwarfs, neutron stars, and smaller black holes will continue to orbit this dark anchor. Over cosmological times, a process called dynamical friction will come into play. As these objects move through the sparse sea of other remnants, they experience a gravitational drag, slowly losing orbital energy. This can cause them to spiral inward over billions of years, eventually merging with the central supermassive black hole. Each merger would provide a final, tiny burst of gravitational waves, a faint ripple in the fabric of spacetime in an otherwise silent cosmos. Furthermore, as galaxies themselves continue their slow gravitational dance, they may still merge long after their stars have faded. When two such ancient galactic structures collide, their central supermassive black holes will eventually find each other, drawn together by gravity and dynamical friction. Their final merger will be a spectacular, if unseen, event, releasing a tremendous pulse of gravitational waves, the last great shout in a silent universe. After such an event, a single, more massive black hole will remain, a silent monument to not one, but two galaxies that once blazed with light. This long-term perspective frames these dark engines in a new light. They are not just the shapers of current galactic structure, but the eventual inheritors and endpoints of galactic evolution. They will be the last objects of consequence, the final custodians of a galaxy's mass and gravitational memory long after its light has faded. While this distant scenario seems inconceivably remote, the processes that lead to it are subtly active today. The dynamical friction that will one day draw stellar remnants inward is the same force that shapes star clusters now. The gravitational wave signatures we are beginning to detect from merging black holes are rehearsals for those final, far future mergers. Studying the quiet, slow dynamics in the core of our own Milky Way today, where stars and stellar remnants orbit Sagittarius, a star, gives us a preview of how a galaxy's final epoch will unfold. This connection between the active present and the silent future reveals the supermassive black hole as the one constant, the enduring thread woven through a galaxy's entire story, from its fiery birth to its ultimate quiet rest. Our own galactic center offers a front-row seat to this cosmic dialogue. The supermassive black hole Sagittarius A star, or Sgr A star for short, is a relatively quiet giant, a slumbering engine compared to the brilliant quasars of the distant cosmos. But its present calm is deceptive. Evidence etched across our galaxy reveals a far more active and recent past. The colossal Fermi bubbles, those immense structures of hot gas towering above the galactic plane, are the monumental relics of a powerful outburst. They tell us that just a few million years ago, a cosmic blink in time, our central engine awakened. It was not a brilliant quasar, but a more subdued yet potent active phase, what astronomers term a low-luminosity active galactic nucleus. During this event, Sgr A star likely launched jets or powerful winds that inflated these gigantic bubbles, a permanent monument to its capacity for transformation. Even today, in its quiet state, its influence is deeply felt. The black hole's gentle gravitational sway heats the sparse gas in its immediate vicinity, preventing it from cooling and collapsing into new stars right at the galactic heart. More dramatically, it orchestrates the motions of the mysterious S-stars, a cluster of young, massive stars that whip around the central void at breathtaking speeds. Some of these stars pass remarkably close to the event horizon on elongated orbits, their frantic dance a direct testament to the overwhelming gravitational presence they orbit. By tracking these stars over decades, astronomers have not only measured the black hole but also mapped the extreme space-time around it, testing the very laws of physics. This makes our galactic center a unique and invaluable laboratory. Because it is so close, we can resolve details impossible to see in distant galaxies. We can study individual gas clouds as they are stretched and heated by the black hole's influence. We can observe how stellar populations are shaped by the environment of the central few light years. This provides essential ground truth, a detailed local case study for the grand theories of feedback developed by observing faraway, more active systems. It allows us to watch the subtle, everyday effects of a supermassive black hole's presence. Our galaxy's current state, a majestic spiral with steady, ongoing star formation, is likely a direct result of this engine's life cycle. Its past outbursts may have helped regulate the core's growth, while its current quiet allows the disk to flourish, and the dialogue is not over. Our Milky Way is slowly interacting with a smaller neighbor, the Sagittarius dwarf spheroidal galaxy. This ongoing minor merger sends streams of stars and, crucially, gas weaving through our galactic halo. Some of this material may eventually find its way inward, potentially providing a future source of activity for Sgr A star and offering astronomers a rare chance to witness the ignition of feedback in something close to real time. We are not just observers of this cosmic story. We live within its sphere of influence, our galaxy's structure and future quietly guided by the presence at its core. But the black hole does not act alone. Its shaping power is exercised within a far larger and more mysterious framework, one we cannot see. To truly understand the cosmic engine, we must account for the invisible scaffolding that holds the entire system together, the dark matter halo. This is the true gravitational anchor of a galaxy, a vast spherical cloud of matter that does not emit, absorb, or reflect light. We only know it is there by its overwhelming gravitational pull on the stars and gas we can see. This immense, unseen structure creates the deep gravitational well that first drew in the ordinary baryonic matter, the gas that would eventually form stars, planets, and the supermassive black hole itself. The properties of this dark matter halo are the ultimate stage directors for the galactic drama. Its total mass dictates how much ordinary gas it can initially attract. Its concentration, how densely packed the dark matter is at the center, influences the density and flow of that gas toward the core. And perhaps most importantly, the halo's merger history, how many smaller halos it has consumed over cosmic time, determines the dynamic, gas-rich events that can trigger both furious star formation and awaken the central black hole. In essence, the dark matter halo sets the table. It determines the quantity and delivery schedule of the fuel that will power both the stellar city and its dark heart. Yet this is not a one-way street. The black hole, through its powerful feedback, can talk back to this invisible framework. While dark matter does not interact with light or with itself in the same way ordinary matter does, it does feel gravity. The incredible outbursts from an active galactic nucleus can heat and push the ordinary gas within the halo, redistributing it. This movement of a huge amount of mass changes the local gravitational landscape. Some sophisticated simulations suggest that this could, over very long timescales, subtly alter the distribution of the dark matter itself, pulling it into a slightly different configuration. There are even speculative ideas that the most powerful jets from a black hole could, in theory, give a tiny gravitational nudge to dark matter particles. This remains a fascinating frontier of research, highlighting how dynamic this cosmic coupling truly is. What emerges is a profound three-way conversation. The dark matter halo provides the foundational gravity. The luminous galaxy of stars and gas evolves within that potential, its gas flowing and forming stars. And at the center, the supermassive black hole acts as a regulator, its feedback influencing the gas and, indirectly, the gravitational environment for all of it. This intricate coupling explains why galaxies are not simple, predictable objects. Their diversity stems from the unique history of this three-way dance within each dark matter halo. This complex interplay is written clearly in the sky, in the stunning variety of active galactic nuclei we observe, each one a unique expression of how matter, both seen and unseen, converses with the engine at its core. This unified engine wears many masks, a true cosmic chameleon. We classify the brilliant, active hearts of galaxies under the umbrella term active galactic nuclei, or a GN, but this family exhibits a spectacular range of personalities. There are the quasars, beacons so luminous they outshine their entire host galaxies, visible from the farthest reaches of the cosmos. Closer to home, we find the milder Seyfert galaxies, where a brilliant core nestles within a clearly visible spiral structure. Then there are the radio galaxies, often quiet in visible light but crowned with colossal, ghostly lobes of radio emissions stretching for millions of light years. For decades, this diversity seemed chaotic, as if each galaxy had its own unique and unrelated power source. The truth, however, is far more elegant. This entire cosmic zoo can be explained by just two simple factors: our viewing angle and the engine's appetite. The key to this unification is a dense, donut-shaped structure of gas and dust called the torus. Imagine this torus encircling the supermassive black hole and its blazing accretion disk, a thick cosmic veil. Whether we see a brilliant quasar or a more obscured object depends largely on whether we are looking down through the hole of this donut or edge on through its dusty walls. If our line of sight is clear, we stare directly into the fiery accretion disk, witnessing the full, dazzling power of a quasar. If we view the system from the side, the thick torus blocks our direct view of the brightest regions, and we see a different, more hidden class of a GN. It is the same engine, just seen from a different seat in the cosmic theater, but there is a second, dramatic actor on this stage, the relativistic jet. The presence and orientation of these powerful beams add another layer of variety. When one of these ultra-focused jets is pointed almost directly at Earth, we encounter the most violently variable objects in the universe, known as blazars. Their light is amplified and scrambled by the jet's incredible speed, creating a dazzling, unpredictable beacon. When the jets are pointed more sideways, they inflate those immense, bubble-like radio lobes we see in giant elliptical galaxies, painting beautiful, faint structures on the radio sky. This unified model is a powerful, simplifying principle. It tells us that the wild variety of active galaxies is not a sign of fundamentally different physics, but of perspective and activity level. A quasar is not a different beast from a Seyfert galaxy. It is simply a more actively feeding black hole viewed from a favorable angle. A radio galaxy with giant lobes is often a quasar viewed from the side, its brilliant core hidden but its energetic jets fully on display. This understanding transforms the AGN zoo from a confusing catalog into a coherent toolkit. By studying a blazar, we probe the physics of matter accelerated to almost the speed of light. By studying a hidden, obscured AGN, we learn how dust and gas are distributed around the central engine. Each type provides a unique window into a different facet of the same monumental process. This multiplicity of perspectives is essential because it allows astronomers to piece together a complete three-dimensional picture of how these engines operate and how their energy floods out in all directions to shape their galactic homes. Yet for all their power, these central engines do not hold a monopoly on creation. The most profound acts of stellar birth often occur far from the core, in the vast, swirling arms of spiral galaxies, driven by a more local and delicate kind of physics. The cosmic engines influence scales down to the smallest galactic scales with surprising force. In the faint, wispy glow of dwarf galaxies, we find a version of the feedback story that is both more intimate and more extreme. These are the cosmic villages, collections of a few billion stars or even less, often orbiting larger galaxies like our own. For a long time, astronomers assumed their central black holes, if they existed at all, would be too small and quiet to matter. Recent observations have shattered that assumption. We are now finding clear signatures of active galactic nuclei, those brilliant central engines, flickering within these diminutive systems. This discovery is revolutionary. It tells us the partnership between a black hole and its home is a universal rule, not a privilege of giants. The drama in a dwarf galaxy plays out on a profoundly different stage. The gravitational well holding the galaxy together is shallow, its grip on gas tenuous. Imagine a small campfire in a fragile paper lantern versus a roaring blaze in a stone hearth. In this low-mass environment, even a modest outburst from a relatively small black hole can have profound, galaxy-shaping consequences. The energy released does not just heat the surrounding gas, it can achieve escape velocity. A single, significant feeding event could propel away a substantial fraction of the dwarf's entire gas reservoir, the very lifeblood for future stars. This is feedback pushed to its ultimate conclusion, not regulation but permanent suppression. A dwarf galaxy subjected to such an event could have its growth and star-forming potential quieted for good, leaving it a faint, aging relic. This process may hold the key to solving some of cosmology's most persistent puzzles. Simulations of our cosmic neighborhood, based on the cold dark matter model, predict that hundreds of small dwarf galaxies should be orbiting the Milky Way. Yet we observe only a few dozen. This is known as the missing satellites problem. Furthermore, the dwarfs we do see seem less massive and less densely packed with stars than the simulations suggest they should be, a challenge called the too big to fail problem. The presence of central black holes in these small systems offers an elegant solution. Early in their history, feedback from these engines could have dispersed gas and moderated star formation, leaving the dwarfs fainter and more diffuse than our models predicted. The black hole, in its fierce youth, may have fundamentally shaped its own host's destiny, explaining why we see so many quiet cosmic villages and so few vibrant small towns. Studying these small-scale engines is like running a cosmic experiment in a controlled environment. The feedback physics is the same, but the host galaxy's ability to absorb that energy is vastly reduced. This makes the effects clearer, more dramatic, and easier to model. It demonstrates that the principles of black hole-driven evolution are not just for the grand spirals and brilliant ellipticals. They operate across the full spectrum of cosmic structure, from the tiniest dwarfs to the largest galaxy clusters, a universal dialogue of gravity and light that shapes everything we see in the night sky. This galactic conversation is written in more than just light and gravity. It is etched into the chemical signature of the stars themselves. The powerful winds and jets launched by an active black hole do not just carry raw energy. They act as immense cosmic freight trains, transporting something far more tangible, the heavy elements forged in the hearts of stars and scattered by their dramatic transformations. This process, known as chemical feedback, is a fundamental form of cosmic recycling. When a supermassive black hole enters its active phase, the surrounding accretion disk becomes a maelstrom. But the material feeding it is not pristine hydrogen from the dawn of time. It is gas that has already been cycled through generations of stars, enriched with atoms like iron, oxygen, carbon, and silicon, the very stuff of rocks and life. The furious outflows capture this enriched material and blast it out of the dense galactic disk. They propel it high into the galactic halo and even beyond, into the vast circumgalactic medium, the sparse gas that surrounds a galaxy like a faint atmosphere. This redistribution has profound consequences. It means that the raw material for the next generation of stars is no longer isolated to the crowded disk. Future clouds that collapse to form stars will do so from gas that has been seeded with these heavier elements. Astronomers measure this through a star's metallicity, the fraction of its composition that is not hydrogen or helium. A higher metallicity means a richer mix of chemical ingredients. By enriching the galactic environment, the black hole ensures that subsequent stellar populations are born with a higher baseline of these elements. This is not a minor detail, it is a crucial driver of cosmic evolution. The metallicity of a star influences its temperature, its lifespan, and the very planets that can form around it. Stars born from metal-rich gas are more likely to host rocky, terrestrial worlds like our own Earth. Consider our own solar system. The iron in our blood, the silicon in our rocks, and the oxygen we breathe were all forged in stellar furnaces and scattered by stellar explosions long before our sun was born. That material had to be mixed throughout the galactic neighborhood. The energetic outflows from our galaxy's central engine during its past active phases likely played a key role in that mixing process. They helped stir the galactic pot, ensuring that the cloud that collapsed to form our sun was already rich with the legacy of countless earlier stars. In this way, the dynamic processes of an active galactic nucleus are directly connected to the availability of the fundamental building blocks for planets and, potentially, for life. The black hole, through its chemical legacy, becomes a silent participant in the story of cosmic complexity, weaving the products of stellar evolution into the fabric of future birth. The quiet giants are not the only black holes shaping the cosmic story. Across the galaxy, their smaller kin, the stellar mass black holes born from collapsing stars, are engaged in their own dramatic dances. When two of these dense remnants spiral together and merge, they do not announce themselves with light. Instead, they send a tremor through the very fabric of the universe, a ripple in space-time known as a gravitational wave. For over a century, these waves existed only in Einstein's equations, an unobserved prediction. Then, in 2015, humanity's ears opened to the cosmos. The LIGO and Virgo observatories, with lasers bouncing down miles-long tunnels, felt the faintest shudder. They had captured the gravitational wave signal from two stellar mass black holes, each about 30 times the mass of our Sun, coming together over 1 billion light-years away. That first chirp and ring down marked the dawn of an entirely new way of seeing. This new sense reveals a hidden population, each merger detected is not just an event, it is a message. The masses and the spins of the merging black holes are cosmic forensic data. They tell us about the lives and final stages of the massive stars that created them, and about the dense stellar environments where they found each other. Did they form together as a binary star system, living and evolving side by side, or were they thrown together later in the chaos of a globular cluster? The gravitational wave data is beginning to answer these questions, painting a picture of how these smaller-scale black holes form and interact within the broader galactic ecosystem. But the gravitational future holds an even grander prospect. In the dense cores of galaxies that have recently merged, the two supermassive black holes can become bound in a binary system, a slow, gravitational waltz that may last for millions of years. Eventually, their orbits will decay, and they will coalesce in the most energetic event since the Big Bang. This merger will unleash a titanic burst of gravitational waves, but at frequencies too low for ground-based detectors to hear. To listen for this, we must go to space. The Future Laser Interferometer Space Antenna, or LISA, will consist of 3 spacecraft flying in a giant triangle millions of kilometers apart, using lasers to sense the subtle stretching of spacetime. It is designed to hear the universe hum with the mergers of supermassive black holes. The implications of such a detection are profound. The energy released in one of these mergers is so immense that it could give the resulting single black hole a powerful kick, a recoil from the asymmetric blast of gravitational waves. In some cases, this kick could be strong enough to displace the black hole entirely from its galactic center. Imagine the consequence: the central anchor, the regulator of galactic evolution, suddenly removed. The core dynamics of that galaxy would be transformed, a silent but monumental change in its governing structure. Observing such an event would give us direct insight into the most dramatic moments of galactic co-evolution. Gravitational wave astronomy, therefore, is not a separate field. It is a complementary sense, allowing us to feel the dynamics we cannot always see. It connects the stellar scale to the supermassive, providing a novel data stream that will rigorously test our models. The chirps from stellar mass mergers and the future hum from supermassive giants will together refine our understanding of how black holes across all scales are both products and shapers of their galactic homes. This new window reveals that the cosmic dialogue is not just spoken in light, but felt in the vibrations of spacetime itself. The universe is not a solved equation. For every elegant law we uncover, like the cosmic connection between a black hole and its galaxy, a deeper layer of mystery reveals itself. The story of these cosmic engines is filled with profound gaps in our knowledge, unresolved questions that both humble and excite the scientific community. Take the very beginning. We have seen quasars blazing when the universe was less than 1 billion years old, their central black holes already weighing billions of suns. The standard model of gradual growth struggles to explain this. How did these giants form so incredibly fast? Did they spring from direct collapse seeds, or was the early cosmos a place of such furious, efficient feeding that our current physics cannot fully describe it? This is not a minor detail. It is a fundamental challenge to our timeline of cosmic evolution, a puzzle whose solution would rewrite the first chapter of galaxy formation. Even the mechanics of the engine's voice remain partly shrouded. We know black holes release energy that shapes galaxies, but the precise chain of events, how the power from the accretion disk couples to and drives those immense galactic winds, is still being mapped. Our most sophisticated simulations must simplify this process, using mathematical recipes to approximate physics too complex to calculate directly. A crucial, often overlooked player in this drama is magnetism. The colossal magnetic fields threading the accretion disk and launching those relativistic jets are fiendishly difficult to model. yet they are likely the very steering mechanism for the engine's most powerful outbursts. Their exact role in focusing energy and determining feedback efficiency is a wide-open frontier. And what of the engine in its quiet state, like our own Sagittarius, a star? We call it a low-luminosity active galactic nucleus, but that label masks our ignorance. The physics of how gas spirals in, or fails to spiral in, at such a low rate is bizarre. The flow is tenuous and hot, more like a diffuse plasma than a smooth disk, governed by conditions we can barely replicate. This is not a dormant giant, but one operating in a strange and poorly understood regime, its quiet hum holding secrets about the default state of cosmic engines. These questions extend into the invisible realm. We have discussed how dark matter sets the stage, but does the black hole's performance alter that stage in return? Could the energetic redistribution of ordinary gas during an active phase subtly reshape the dark matter halo itself? This potential two-way conversation between the seen and unseen components of a galaxy is a thrilling, speculative area of research, probing the edges of known physics. Perhaps the deepest mystery lies at the very boundary of the black hole itself, at the event horizon. The famous black hole information paradox, a conflict between quantum mechanics and general relativity, asks a seemingly simple question with universe-shaking implications. When matter and information cross that threshold, what is their ultimate fate? The conservation of quantum information suggests a profound puzzle, hinting that our understanding of space, time, and reality may be incomplete. Resolving this paradox may require a theory of quantum gravity, a unified framework that could utterly transform our conception of what a black hole actually is. These are not mere technicalities, they are fundamental cracks in our understanding, through which we may one day glimpse a new kind of physics. Far from being discouraging, these unsolved mysteries are the lifeblood of discovery. They are the compelling questions that launch billion-dollar telescopes and inspire generations of theorists. Each unknown is a destination on the map for future exploration, a reason to build more sensitive detectors and more powerful supercomputers. The story of cosmic engines is not a finished book. It is a living document with its most revolutionary chapters likely still unwritten, waiting for the next observation, the next simulation, the next brilliant insight to turn a baffling mystery into a cornerstone of understanding. The frontier of this cosmic dialogue is about to be illuminated by a new generation of explorers. Our quest to understand black holes as galactic architects is accelerating, powered by an unprecedented fleet of observatories, each designed to perceive a different facet of the story. In the coming years, these instruments will transform our view from isolated snapshots into a high-definition movie of black hole and galaxy co-evolution. They will test our theories with precision data and, without a doubt, reveal surprises that will once again redefine the role of these dark engines in cosmic history. Already, the James Webb Space Telescope is acting as a time machine, peering into the hearts of the universe's first galaxies. Its infrared gaze cuts through cosmic dust to study the earliest black hole growth, probing that mysterious era when these giants assembled with astonishing speed. It seeks to catch them in the act of shaping their infant homes, watching the first words of the cosmic conversation. To complement this deep, focused view, the upcoming Nancy Grace Roman Space Telescope will conduct sweeping, wide-field surveys of the sky. It will not study one galaxy at a time, but millions, building powerful statistical links between active galactic nucleus activity and the properties of their host galaxies. This big data approach will reveal the universal patterns in the feedback process, showing us the rules that apply across the entire cosmic population. To feel the heat of the conversation, we will turn to the Athena X-ray Observatory. This mission will map the superheated gas in galaxy clusters with breathtaking detail, measuring the temperature, density, and motion of the plasma with precision never before possible. It will watch how black hole-inflated bubbles rise and dissipate their energy, allowing us to calculate the exact thermodynamics of feedback to measure the energy budget of these cosmic regulators. Meanwhile, on the ground, the square-kilometer array will use thousands of radio dishes to trace the invisible architecture of cosmic magnetism. It will map the faint glow from relativistic jets and their interactions with intergalactic gas on the largest scales, revealing how magnetic fields channel and focus the black hole's most powerful outbursts. Closer to home, the extremely large telescope will use a mirror nearly the size of a baseball diamond to gather light. With this immense power, it will directly image the frantic motions of stars and gas around nearby supermassive black holes, including our own Sagittarius, a star. This will refine our mass measurements to exquisite accuracy and allow us to test gravity in its most extreme regime, watching how individual stars are guided by the profound gravitational influence. And from the quiet of space, the laser interferometer space antenna will open an entirely new sense. This formation of 3 spacecraft will detect the low-frequency hum of spacetime itself, listening for the mergers of supermassive black holes. It will hear the final moments of binary giants coming together, events that could profoundly alter a galaxy's core and forever change its future path. Together, this symphony of instruments represents a holistic approach to a holistic problem. We are no longer relying on a single telescope or a single wavelength. We are building an interconnected sensor network for the cosmos capable of seeing the gas, tracing the magnetic fields, weighing the black holes, and hearing their mergers. This multi-messenger era promises to weave a complete narrative. We will move from inferring the dialogue to witnessing its mechanics in real time across the full history of the universe. The data flowing from these missions will either beautifully confirm our models of cosmic feedback or, more excitingly, reveal flaws and gaps that point toward new, undiscovered physics. The story of how black holes shape galaxies is entering its most thrilling chapter, driven by tools that will let us see, hear, and feel the universe in ways we have only dreamed of. This cosmic perspective does more than explain galaxies, it redefines our place within them. For centuries, we saw the universe as a static stage, a beautiful but unchanging backdrop against which the human story unfolded. The stars were fixed points of light, the Milky Way a serene river of distant suns. The discovery that a supermassive black hole governs that river, that its ancient activity sculpted its very shape and paced the birth of its stars, transforms that passive view. We are not living on a quiet stage, but within a dynamic, evolving system whose history is written in the echoes of a central engine's past activity. The majestic spirals and glowing ellipticals are not immutable sculptures. They are living records of a continuous, self-regulating conversation, a ballet of forces where the unseen choreographer sits in profound darkness. This narrative weaves together every scale of existence: the destiny of a single star, the flow of galactic gas, the unseen grip of dark matter, and the very curvature of spacetime are all participants in this grand cosmic dialogue. The implication is profound. The conditions that allowed our solar system to form, that provided the right mix of elements and a stable galactic neighborhood, may not be accidental. They could be the indirect legacy of our galaxy's central black hole. Its historical activity, through cycles of feedback, helped regulate the rate of star formation, preventing a frantic burst that would have consumed all the fuel too soon. Its powerful outflows helped mix and distribute the heavy elements forged in stellar hearts, seeding the galactic disk with the chemistry necessary for rocky planets. We are, in a very real sense, living in the aftermath of that story. Our sun, our planet, and the atoms that compose us are products of a galactic environment that was, in part, shaped by an invisible force 4 million times the mass of our sun, sitting 26,000 light-years away. This understanding transforms the black hole from a distant curiosity into something far more integral. It is a central player, a fundamental agent in the universe's long journey from the simplicity of the primordial fog to the breathtaking complexity of spiral galaxies, planetary systems, and life. The event horizon, a boundary of such profound mystery, is connected through chains of cause and effect to the largest structures we can observe. This realization is both humbling and awe-inspiring. It tells us that the laws of physics link the infinitesimally small with the grand architecture of the cosmos in a continuous, unbroken thread. Our home galaxy is not just a collection of stars we happen to inhabit. It is an ecosystem, and we are within its web, connected to a history of colossal forces and a future shaped by a silent, dark heart. This shifts our cosmic address from a random point in a static void to a participant in an ancient, ongoing story of creation and balance. Our journey reframes these cosmic giants from destructive forces into creative architects. They are the universe's ultimate regulators, the hidden engines that drive galactic evolution across the vast expanse of time and space. We have traced their dialogue, a conversation written in the language of gravity and light. Their cyclical feedback can quiet a galaxy's starry fires or, in a brilliant paradox, ignite new waves of stellar birth. Their powerful outbursts sculpt majestic spirals into smooth ellipticals, govern the hot atmospheres of galaxy clusters, and seed the cosmos with the heavy elements essential for planets and life. The elegant cosmic law linking their mass to their galaxy's core, and the fossilized bubbles towering above galactic disks, all whisper the same truth. This is a profound, symbiotic partnership. The dark heart and its stellar city grew up together, shaping each other's destiny in a constant, dynamic exchange. While profound mysteries linger at the event horizon and in the cosmic dawn, the overarching narrative is now unmistakable. To truly understand a galaxy, its shape, its history, and its future, we must listen to the voice of its central black hole. As we stand at the threshold of a new era of discovery, with telescopes that will see further and feel more deeply than ever before, we are poised for even more transformative revelations about these fundamental engines. So the next time your eyes lift to the starry band of the Milky Way arching across the night sky, remember this: you are not just looking at a random scattering of distant suns. You are witnessing a grand, dynamic structure, a cosmic ecosystem whose very form and rhythm have been quietly guided across billions of years by the silent giant at its core. If this exploration of how black holes shape the cosmos captivated you, please subscribe for more journeys into the deepest mysteries of space. We would love to hear your thoughts on these cosmic engines and the future of galaxy evolution in the comments below.